Hey everyone, welcome back to The Explainer. So think about your morning routine for a second. You drop a spoonful of sugar into your coffee, give it a quick stir, and boom, it just completely vanishes. Or maybe you're making pasta, you toss some salt into boiling water and it disappears without a trace. It feels like an everyday magic trick, right? But there's actually this massive invisible dance of molecules happening right in front of us. Today, we're going to demystify the whole process. We're breaking down the exact mechanics of how things dissolve, the hidden energy it takes to make it happen, and the incredible invisible forces governing the liquids we interact with all the time.
It's the ultimate question, isn't it? What actually happens when a solid seemingly disappears into a liquid? Where does it go? To truly wrap our heads around this everyday mystery, we have to take a journey. We're going to start at the macro level, the stuff we can literally see with our own eyes, and then we'll zoom way down to the micro level to witness the atomic tug-of-war that's taking place. After that, we'll zoom back out to see how all of this impacts our world on a massive scale.
Here is our roadmap. Number 1, the process of dissolution. 2, the energetics of solutions. 3, the nature of electrolytes. 4, exploring solubility and saturation. And finally, number 5, temperature, pressure, and Henry's law. Let's get right into it.
Section 1. The process of dissolution.
When we talk about solutions, we've got a solute, that's the stuff being dissolved, like our sugar, and a solvent. The solvent is the medium doing the dissolving, and is usually there in a much larger amount, like water. Now, honestly, a lot of us just assume solutions have to be liquids, right? Like solid salt dissolving into liquid water. But wait, did you know air is actually a gaseous solution? It's oxygen dissolved into a nitrogen solvent. And brass? It's a solid solution of zinc dissolved into solid copper. Basically, as long as the mixture is entirely uniform on a molecular level and won't settle out over time, it's a solution. It literally doesn't matter if it's a gas, a liquid, or a solid.
Section 2. The energetics of solutions. Okay, so we know what a solution is on the macro scale, but let's zoom in. Because breaking apart a solid and perfectly blending it into a liquid doesn't just happen magically. There's a very strict energy transaction taking place. Think of it as a 3-step process. Step 1. You have to shatter the bonds holding the solute together. Imagine pulling apart tightly packed salt crystals. That requires energy, which makes it an endothermic process. Step 2. You got to make room in the solvent. You physically push the water molecules apart to fit the salt inside. This also takes energy, so, yep, endothermic too. But step 3. This is where it gets interesting. The solvent molecules rush in and surround the solute particles. They establish brand new attractions. Forming these new bonds actually releases energy, meaning this final step is exothermic.
And that brings us to an absolutely crucial definition: solvation. Solvation is that highly rewarding exothermic third step where energy is released as the solvent embraces the solute. Now, you might be wondering, why do some solutions get physically hot or cold in your hand? Well, it depends entirely on the balance of this energy transaction. If the energy released during solvation is greater than the energy required to break the initial bonds, the whole process releases heat. It gets warm. But if it takes way more energy to shatter the original bonds than what you get back during solvation, the process actually absorbs heat from its surroundings.
Which brings us to a brilliant real-world application: instant cold packs. When you crack one of those cold packs, what you're really doing is breaking a tiny pouch of water inside a bag of solid ammonium nitrate. The ammonium nitrate starts to dissolve, but its initial bonds are so incredibly strong that breaking them requires way more energy than is released during solvation. It literally steals heat from the environment, which is exactly why it feels freezing cold on your injured knee. But hold on, if it costs so much energy, why does it even happen at all? Well, it happens spontaneously because of entropy. The universe has this fundamental, relentless drive for increased matter dispersal or disorder. The drive for these molecules to spread out and make a messy, uniform solution is so amazingly strong that it overpowers the steep energy cost.
Section 3. The nature of electrolytes.
We've seen the energy dance, but what happens when the particles we dissolve carry an actual electrical spark? If we hook 3 distinct solutions up to light bulbs, we can literally see this invisible world proven visually. Take ethanol, for example. It provides no mobile charges at all. It's a non-electrolyte. It dissolves into neutral molecules, so the bulb stays completely dark. But look at potassium chloride, or KCl. The bulb is blazing bright. KCl is a strong electrolyte, meaning it yields a massive concentration of freely mobile ions that just perfectly conduct electricity. Then with acetic acid, it gives us a pretty dim bulb. That makes it a weak electrolyte, where only a tiny fraction of it actually produces ions.
So how exactly do these charged ions get into the solution to light the bulb in the first place? Well, there are two completely different mechanisms here. First, we have dissociation. This happens with ionic compounds. The ions already exist inside the solid crystal. The solvent just physically pulls them apart. It's a purely physical change. Then we have ionization. This happens with covalent compounds, like certain acids. These compounds don't even contain ions to begin with. Instead, they undergo a literal chemical reaction with the water molecules to generate entirely new ions from scratch.
Let's look a bit closer at dissociation, because this is absolutely the primary mechanic for strong ionic electrolytes like salts. Dissociation is purely a physical separation. The ions in the solid structure are forcefully separated and dispersed because the solvent molecules literally surround and isolate them. They basically neutralize that strong electrostatic glue that was holding the solid together. And here's exactly how that physical teardown happens to a solid block of potassium chloride when it gets attacked by water. You see, water is a polar molecule. It has a slightly positive hydrogen end and a slightly negative oxygen end. Notice how the negative oxygen ends of the water molecules are swarming the positive potassium ions, while the positive hydrogen ends of the water are grabbing onto the negative chloride ions. The water molecules effectively gang up on the individual ions, reducing their attraction to each other and just plucking them off the crystal one by one, letting them float away independently. It's wild.
Section 4. Exploring solubility and saturation.
So water is obviously a highly effective solvent. But zooming back out to the macro level, we kind of have to ask, is there a limit? How much can it take before it says, nope, I'm full? This capacity limit actually gives us three distinct states. An unsaturated solution means there is still room at the end. If you add more sugar, it's going to dissolve. A saturated solution means the concentration has hit its absolute natural limit. If you add even one more single grain of sugar, it will literally just sink to the bottom and stay there. But then, there is the supersaturated solution. Under very specific conditions, you can actually trick a solvent into holding way more solute than it naturally should, but it is a highly delicate, non-equilibrium state. It's exactly like a loaded spring. The slightest disturbance can cause all that excess solute to crash right out of the solution instantly.
Section 5. Temperature, pressure, and Henry's law.
Now, those saturation limits we just learned about? They aren't fixed. External variables can completely rewrite the rules. Let's start with temperature. The general rule of thumb is that as a liquid gets warmer, dissolved gases become less soluble. They basically want to escape. If you leave a glass of cold tap water out on your counter, you'll see those harmless little air bubbles form as it warms up to room temperature. But think about this on a massive scale. If an industrial plant dumps artificially warmed water into a river, that sudden heat dramatically decreases the solubility of oxygen in the water. The oxygen just escapes right into the atmosphere, totally suffocating the aquatic ecosystem and causing massive, tragic fish kills.
So, temperature is clearly a major factor. But for gases, pressure is just as critical. And this brings us to Henry's law. Henry's law states that the quantity of an ideal gas that dissolves in a definite volume of liquid is directly proportional to the pressure of that gas hovering right above the liquid. Simply put, if you squeeze the gas with high pressure, it forces those gas molecules to dissolve right into the liquid, which perfectly explains the everyday magic of a carbonated soda. When a soda is bottled at the factory, they pump carbon dioxide into the neck of the bottle at incredibly high pressure. This forces massive amounts of the gas to dissolve into the liquid, creating one of those supersaturated solutions we talked about earlier. The moment you twist that cap off, you hear that familiar hiss. That is the high-pressure gas escaping. And according to Henry's law, because the pressure above the liquid just dropped, the solubility of the liquid drops instantly too. The liquid literally cannot hold the gas anymore, and the carbon dioxide violently escapes in a giant rush of bubbles. So the next time you pop open a soda or stir sugar into your tea, ask yourself, what invisible atmospheric pressures and microscopic forces are shaping the liquids around you right now? Thanks for joining us for this explainer, and keep questioning the world around you.